Andreas. Yeah. Hello, everyone. I'm very happy to be here. This is my first time at TYPES, and everyone said that it's a great conference, and I agree. I'm having a great time. This is a very, in some sense, very simple, very simple little result. In summary, in one sentence, I can summarize what we did. This is joined by with the Robbert Krebbers. What we did was provide some new rules for commuting the later modality with quantifiers, and this rule is sound with respect to the semantics in the tables of trees. And if you know what these words mean, then you will understand these rules. And yeah, they look a bit complicated, but essentially this is what happens. But of course I'm going to explain in a bit more detail and provide some background for the whole story. And everything is formalized in Rock, so that's nice. So let's start with some context. So the question that Gaudian recursion tries to solve, or the question that this whole research is about, is how do we ensure that the recursive definition is well defined? And yeah, here are some examples. For example, we can define the factorial function recursively as follows. I think everyone knows this definition. Similarly, we can define a function which increments every element of a sequence by 1. And also we can also define this recursively as follows, where we first increment the first element of the sequence and then increment the tail of the sequence recursively. And so these are recursive definitions, but how can we ensure that these are actually make sense? And there have been multiple solutions to this problem, proposed solutions. And the first one that I think everyone knows is the idea of inductive data types. So here's an example of an inductive definition in Agda. So the idea here is that we ensure that the recursion is well defined by defining the domain that we are using defining recursion over to be some kind of a well-structured domain. And in the case of inductive types, this means that we can construct every element from in exactly one way from constructors. And then in the recursive call, we can only refer to subterms or terms which are in some sense smaller than the original term we started with. So because we decrement the size of the input in the recursive call, we can ensure that the definition eventually terminates. So this kind of pattern encodes well-founded definitions, recursive definitions. The second solution, which is maybe less well known but still useful, is the idea of co-inductive data types, which is kind of in some sense dual, at least categorically speaking, dual to inductive types. So here, instead of saying how to construct elements of a data type, we tell how to destruct elements of data type. So the canonical example for co-inductive data type are streams. Infinite streams of numbers, let's say, and the streams are defined by having a head, which is a natural number, and a tail, which is again a stream, a co-recursive occurrence of the stream, and you can define functions on streams by co-recursion. And in Agda, we would write this increment function that I mentioned earlier, like so. The head of the incremented stream is just the successor of the head of the input. And the tail of the incremented stream is the incremented version of the tail of the input. And here what is key is that this definition is productive. So no matter what the input is, even though the input is not well founded because it's infinite, still the way the recursion is defined, in every step we produce we produce something, so therefore there is no infinite. There will be no case where we don't know what to do next, basically. So that's the idea. And so both of these solutions suffer from some restrictions, namely that these inductive and quantitative types are usually supposed to be strictly positive in order to guarantee termination, which is some syntactic restriction on the type. But what if you want some more exotic domains, such as this one, which is some higher order syntax for lambda calculus? So this is an example in Haskell. This will not type check in Agda, for example. So a third solution, which was proposed at this point about 25 years ago, is to use the idea of stepwise approximation to define recursive to make sense of recursive definitions. Some history for this is that first this was done purely semantically, which involves tedious calculations, but then Nakano created a model framework for working with these self-referential formulas and definitions. And later, these two branches of work was also married, and hence Gaudian recursion was born. So let us talk about what Gaudian recursion is, or what the idea of Gaudian recursion is. So the idea is that we introduce a new type former modality, which we call later, but the intuition is that it allows us to talk about data that we only have access to in the next step. And in practice, what this does is that it allows us to guard recursive occurrences in recursively defined types and terms, and this guard is what will allow us semantically then to ensure that the definition is well defined. So what we need to know in practice about this type former or memory programming is that it admits an applicative structure, so we can take some data that we have constructed and shift it into the future. That's what the next does, and we have this applicative application operator, which allows us to apply a function under the later modality in the future. And a very important thing in this setting is that we have a fixed point combinator, which is very surprising in type theory, because usually that implies a non-termination. But notice the type here, that the type of the function we take the fixed point of has this type of later A to A. So somehow the recursive occurrence is shifted in time by one step, and that's what makes the definition well-founded. So an example. An example for Gaudian recursion are streams. So we define a type which is fixed point of this type function. So we have a natural number and which is the head, and the stream which is the tail. But notice that the recursive variable is guarded under a later. And then we can program with this type using constructors and destructors, cons and head and tail. And the recursive, the fixed point combinator. So for example, we can define the stream of zeros or the function increment, which increments every element by one, as shown earlier. So this is programming. Now, what about logic? So, under the query-house correspondence, we can think about this later modality also logically, and then we get some new construct. We get a logical modality which intuitively expresses that some proposition holds later in time at the next step. And then the applicative structure that we have for the later type former gives us some model axioms, which are pretty standard. And the fixed point combinator gives us the Löw rule, which is some kind of powerful induction principle, which allows us to prove some proposition, assuming that the proposition holds one step later. It's called the Löw rule because the shape of the the rule is similar to the provability, the Loeb's proof of the probability of formulas that we've seen earlier.
Jump to conclude.
So I think I have 5 minutes left. We started at 22.
Okay.
Well, I can speed up. Okay, well, we can skip this. Well, okay, I wanted to talk about semantics, a bit about the semantics of the step index logic as well, to give some intuition about what all this means. But I mean, it's not, if in interest of time, if you want more coffee, then I can I can skip that. Yeah, I guess I would just say that the semantics is for this logic is provided by the topos of trees, which are pre-sheaves on natural numbers. So this means that everything is indexed by natural numbers. So everything depends on this step index, and basically the recursive definitions are then become well founded by recursion on this step index. That's the main idea. And then the later type former just shifts everything one to the future. Here's the example. And the logical aspect of this this story is that the semantics of the logic that I just presented in this topos is essentially quickly semantics over natural numbers. So the truth of proposition depends on the step index. Intuitively, this means that truth values are downward closed subsets of step indices. And we have this later modality on propositions, which essentially just increases the truth of a proposition by 1. And very importantly, this later modality satisfies this property. There's a typo there, that later p, the formula later p is true at step n plus 1 if the formula p is true at step n. So it again shifts the truth of a proposition one step into the future. So now we arrive. So now with all this context in hand, we arrive what the actual contribution is that how can we devise rules which commute the later modality with the quantifiers. So we can prove these rules very easily from other principles, but the other directions, the right to left directions are not valid, and the reason for that is essentially because in the two sides we are quantifying over different domains, and so therefore we might miss some elements on the left side. And in the literature, there does not seem to be a general commuting rule which solves this problem. And so what people have been doing so far is require some semantic condition on the type on the domain of quantification, namely this condition of being total and inhabited, which is a semantic condition, but it can be expressed internally as a formula. So therefore, if we assume this condition, then we get the converse direction as well, which is nice. But of course, the issue is that this only works for some subclass of types, so that's not satisfactory. By the way, we can move the assumption of total inhabitedness into the precedent of the sequent. So the main observation, 1 minute, the main observation then is to solve this problem is that we can decompose the data modality, which was observed by Birkedal and also Clausen, into two components. One of which is this lift operation, which has a different type than the data modality, and it somehow extracts the essence of the idea of shifting to the future but gives it a stronger type. And therefore, the idea was that we can investigate how this quantitative interacts with the quantifiers. And well, the claim is that these rules are actually sound. And they look complicated, but basically, if you just replace the data modality with this lift and then make sure that everything type checks, there's only one way to do this. A key point here is that on the right hand side, we're quantifying over later A and not A. So that's what solves the issue of quantifying over different domains. And these rules are sound, and they imply previous rules, so they are actually more general, which is nice. And yes, that's it. And yes, thank you.